welcome to Sharks with Lasers on Their Heads. My name is Eric Steinoff. I'm an assistant professor here in the Department of Physics and Astronomy, and by all means interrupt me at any point. So what I'm hoping is that we can learn about lasers today and learn some of the materials and properties of lasers. Everyone in here is probably today and every day has lasers in their life at some point. What is a laser? Does anybody know what the word laser stands for? The letter L actually stands for light. It turns out the word laser is actually an acronym where each letter means something. It's light amplification by stimulated emission of radiation. Well, the idea is that I've got a bunch of atoms or different types of things that are all excited. They're all hyper and ready to go, and they want to emit light. They're just in an excited state, ready to go. They want to send out some light. And what will happen is one of them will actually do that. It'll relax down and send out a photon, which is a piece of light. That photon will pass by another atom and stimulate that atom to emit. So there's the stimulated emission. And that atom will then send out its own photon, and those two are going to move together. They go up and down at the same time. This is for us known as in phase. And this is what gives light, this word down here, the word coherent. Laser light is coherent. All of the photons, all of the light is moving up and down at the same rate. Now, what I need to do then is I need a material that I can excite that will emit light and stimulate other atoms to do the same. So here I've got basically a helium neon laser. This is one of the first gas lasers that were produced. And you'll notice that I've got this beam in the middle here, and what's happening is there's two mirrors on the end, and the light is going back and forth, and on the end it's very weak, unfortunately. There is laser light coming out. Now, one of the other things that is very important about lasers is the fact that it's a very pure color. Look at my green laser pointer. It's green, very green. And this is what's known as monochromatic. Mono meaning one, chromatic meaning color. Why is the wavelength important? Well, I told you that you get a shorter wavelength when I get blue. A shorter wavelength means that I can actually see things, smaller things. I can see smaller objects with a shorter wavelength. So here I've got a piece of plastic, I send the beam through, it goes straight through, great. But what if I bend it a little bit? Is light going to escape? Turns out no, it bounces along. So can you see it bouncing and making a little V there?
Yeah, that's awesome.
So this is basically how fiber optic works. So the light bounces around inside of this glass light pipe, which is what a fiber optic is. Nobel Prize was awarded for the physics inside of this a few years back. And this is how our information is transmitted over long distances. In the name of science and reproducing someone else's results, I decided to try and pop some popcorn. Now, I'm going to start this movie, and I want you to keep in mind that this is real time. When I start the movie is when I turn the laser on. I've got one kernel of popcorn. I've wrapped it in aluminum foil. The reason I did that is if I don't, it actually just burns the popcorn. It just starts catching fire and smoke. So I put it in aluminum foil. And here I go. I'm going to start the movie. See how long it takes to pop this popcorn. Now, the other thing I want to say is, this is the laser I have up at my lab. This is a 10-watt green laser. That's 2,000 times more powerful than this laser pointer. And it took probably 20 or 30 seconds for it to pop. Now I know you may have missed it, I missed it. So I'll play it over and over again. Here's the quick one. See, it blows up and pops. So I'm going to turn on my big powerful blue laser here. Stays on, okay, and here we go. We're going to, I'm tracking. Whoa, there we go. So I am able to light a match very quickly, as a matter of fact, using my blue laser. I have a blue laser. I have a blue balloon which reflects blue light. Nothing happens. Orange balloon. Why is it orange?
Because it is.
It reflects so much light.
It reflects orange light, absorbs all the others. So let's see what happens with the. Whoa. Wow. Last but not least, I told you I was going to tell you how we use this here at OU. We use this to do science. What I do, very simply, so I tell my mom what I do, is I shoot lasers at things and I look at the light that comes back. So I'm going to give you an example of that over here. So I shoot a laser at this piece of paper, and you can see that it gets very bright. So I'm hitting this with a very UV laser. In fact, if I go over on the black, you can't even see it. It's very hard to see it. It's very hard to see over here. But if I hit the paper, I get light that comes back at me. That's luminescence. So I'm looking at the light that's coming back at me. And so I hit it with the laser, I get some light back, and I can study it. Well, this is not the only thing that I can get back. I can get other materials, for example, like this, where I'm using phosphorescent materials. So the light goes in and it gets stored. This is like the stars you have on your ceilings, for example. The light goes in, it gets stored, and notice it comes back in a different color. It's coming back green. I'm sending it blue, and I'm getting a longer wavelength, green, at a lower energy. By looking at the light that comes back, I can tell something about that material. I can also tell something by how long it takes for the light to come back. I can tell stuff by the polarization of the light. So a lot of what we do is studying light going in and light coming out of a material, and it gives us a lot of information.